Hey guys, welcome back to Problem Up Chem, and we're gonna build on some of the stuff we've been doing with electrolysis and look at advanced electrolysis, focusing on the electrolysis of solutions. So let's get started. Now, in this lesson, we're going to be looking at why electrolysis of aqueous solutions is different, how we can predict the outcome, and then we're going to look at evaluating quantitative electrolysis. But first things first, as usual, there's a question to refresh from last lesson. Then pause the video here to give yourself some time for that. Okay then, so with this equation, we're going to be using our delta G equals negative NF multiplied by E cell that we did last time. And we know that there's 2 electrons multiplied by Faraday's constant multiplied by 1.61. So we're going to get minus 310,730, and I'm just going to divide that by 1000 to give me the answer in kilojoules, which is minus 310 kilojoules. Awesome. So the key for us understanding electrolysis of solutions is understanding that water itself can be electrolyzed. All we need to do is add some protons so we can aid the current conducting. So this is split into 2 reactions. At the anode, where we always have oxidation, remember, we get the reaction, remember these are in your data booklet, of oxygen plus H plus and electrons goes to H2O, and that has a value of plus 1.23. Now remember, it's going to go left, and at the cathode we have the reduction. This is where we're going to get H2O plus electrons goes to H2 gas and 2OH minus, which has a value of minus 0.83 volts. Now, if we think about the overall reaction here, we have to take into account the oxidation reaction. So our overall reaction is going to be 2H2O goes to 2H2 gas plus O2 if the electrons are cancelled out. And actually, going in the opposite direction here is the reaction that makes up a hydrogen fuel cell. So knowing these 2 reactions are going on is going to help us with working out our electrolysis of aqueous solutions, because we know we're going to have competing reactions at each electrode. We're going to have water and whatever other ions are in the salt that is dissolved in the water. And this is really where we have to spend our energy. We're going to look at our trusty E cell values, and we're going to work out which will be discharged. So let's have a look at what we have to consider. We have to consider 2 areas. Okay, so let's have a look at the cathode first. You are going to need to make sure you have your copy of your data booklet looking at table 24, which is your standard electrode potentials. So at the cathode, we need to consider reduction, of course. So we're going to look at our E cell values, and if you have an E cell value that is more negative than the reduction of water, that's 0.83 volts, then water is going to be reduced instead of the cation. So you're looking for anything that is more negative you can ignore. This includes metals such as lithium, potassium, magnesium. All of these are in this area. If you look at your values, you'll see that value for water, negative 0.83. Anything above that will not be discharged, but anything more positive than water will be discharged. Now at the anode, we're going to have to consider the oxidation reaction. So remember, oxidation reaction is going to be the inverse of what's on your tables. So if the anion has a more positive E cell value than 1.23 volts, water will be oxidized instead of the anion. So this is things like fluoride and sulfate. They will not be oxidized because these are past the value of water. And all you have to do here is you think anything below that value of plus 1.23, so anything that has a higher value there on your table will not be oxidized, but anything above, anything that has a more negative value than the water will be oxidized. So you can think about your overall table as excluding anything above and below those two values for the reduction and oxidation of water. Now, there are some exceptions to this rule, and we're going to look at brine to try and illustrate this. Now brine is NaCl. Now, chlorine has a E cell value, a potential of plus 1.36 volts. So we of course think, well, in this case, water will be more likely to be oxidized. However, this isn't the case that we see when we electrolyze high percentage solutions of brine, of NaCl. So it should not be discharged. However, we do end up getting some chlorine gas. So this is due to a thing called overpotential. We don't need to go into that for IB, but if you would like to have a little look at it online, you can. Basically, it just means that something different from the standard potential happens when we do it in practice. What happens is we get chlorine gas discharged when we have concentrated solutions of brine. So NaCl or brine solutions, when we have a concentrated solution that's above about 20-25%, we would expect the oxidation of water, but instead we get the oxidation of chloride ions to form Cl2. And again, that's only in concentrated solutions. Now we get chlorine gas produced. Chlorine gas is relatively soluble in water, so we get a varying amount of that in solution. Some of it goes into solution, some of it comes out as a gas. So if we're asked what we would expect the products of an electrolysis to do, we can use the same 4-step method we introduced in the SL component, but we're just going to elaborate on that second step, what reaction is occurring at each electrode. So let's have a little look at an example. Let's take lithium fluoride, and so at the cathode we're going to have the reduction of water. So we're going to have water forming H2 plus OH minus, which is going to have negative 0.83, and that's always going to be the reaction that's competing at the cathode in aqueous solutions. And we've also got lithium, which is also looking to be reduced. Now, you can get these values from your table. You should have your table alongside while we're doing these questions, and we can see that because this is a reduction potential, we can see that lithium has a lower value than the water, aka it wants to be reduced less, and because it wants to be reduced less, we know that water will therefore be reduced in this case. Now, it's important to remember that when we start looking at the anode, that we are thinking that the reactions are going to go in the reverse direction from how they're written in the data booklet. So we obviously have our oxidation of water reaction here, which has a value of plus 1.23 volts, and we're going to compare that with the fluoride ion. So we're going to be looking at the oxidation of fluoride ions into fluorine gas, and that has a 2.87. But remember, these go from right to left, so we are going to invert these values. So we can see now that the less negative or the more positive value is the one that will occur. So combining those two equations, after we flip the reaction for the oxidation of water, we're going to get our 3 moles of H2O form H2 to OH minus, half O2 and plus 2H. Now remember, plus combine the hydroxide and the H plus, which makes water, and then we cancel out the overall water, is going to leave me with H2O goes to H2 plus half O2, which is the overall electrolysis of water. Okay, let's have a look at another example. So we're going to use lithium chloride, and we're going to use a concentrated solution. So at the cathode, remember, we're going to have reduction at the cathode, and we're going to have our reduction of water, as we always will in electrolysis of aqueous solutions, which has a value of minus 0.83 volts, and we have the reduction of lithium equation, which has a value of minus 3.04. So just as before, this value is less than that from going left to right of the water, and so therefore water is going to be reduced and water will be electrolyzed at the electrode. For the anode, again, we have our equation for our oxidation of water, which is going to have a value of plus 1.23 volts. And this time we have chlorine, which for the oxidation of chlorine, which is plus 1.36. So using our rules, this would mean that the water will of course be oxidized. However, we know that because we've got a concentrated solution of lithium chloride, our overall reaction is going to include the oxidation of the chloride ions. So we get water plus Cl minus gets half Cl2 plus half H2 plus OH minus. When we think about the last step then, we want to consider our qualitative observations. So we can see here, we're going to produce chlorine gas at our anode, and we're going to produce hydrogen gas at our cathode. That's a clear gas and a green gas respectively. And the solution will exhibit an alkali pH because of the production of the OH minus ions. So let's have a look at one more example before you try some questions on that. A common one, which is copper sulfate solution. So at the cathode, once again, you're going to have your reaction for the reduction of water, as we have in every solution, which is minus 0.83. But now we have copper being reduced, which is plus 0.34. So you can see here that we're going to actually form the copper solid. We're going to have the copper being reduced instead of the water, the cathode. Coming over to the anode, this is the main reason I chose this example. We have the water as always, but on your table, on your data booklet, you will not actually find the correct equation for the oxidation of the sulfate ion. I'm not actually fully sure about the equation for this oxidation. I had a little look online, I couldn't shore it up, but I think it would look something like this. A couple of people suggest online that it might be something like this. This is not the correct equation. Do not confuse the equation in the data booklet that has the sulfate ion in, because that is for the reduction of the sulfate ion and you would need it for the oxidation for the anode. So every time you see this sulfate ion, you can assume that the water will be oxidized. That gives us an overall equation of water reacting with the copper then. So that's just why I wanted to give you an example of a sulfate solution, because it's probably just going to be easier for you to remember that anytime you have a sulfate solution, you're going to have the oxidation of water going on at the anode, and not to confuse what is on the data booklet. Let's have a go at some questions to see how you're getting along with this. First question, when you do for the electrolysis of copper bromide, what would be the products discharged at the anode? Pause the video here to give yourself a moment for that. Pop them up! So first things first, you're going to need the reactions at each electrode. So at the cathode, copper is going to be reduced because it has a more positive value than that of water. And at the anode, you are going to have the oxidation of the bromide ions, because the bromide ions have a more positive value in the reverse direction than that of water. So you're going to get bromine gas formed at your anode, and then you're going to get copper solid at the cathode. So for the next question, I want you to write the overall reaction for that equation. Pause the video, give yourself a moment for that. Pop them up! So because we've already done the earlier question for this, we're just going to need to make sure our electrons are balanced for our two half equations, and they're also the correct way around. So you'll see I've flipped the bromide equation and multiplied it by 2. Now the electrons cancel, and you add the two equations together, giving us the bromide plus copper ions go to bromine and copper solid. Now, all of this can take a bit of time to get used to and process multiple different parts of a question or parts of an equation. So here are some questions that I just want you to practice on for predicting the products of the anode and cathode for aqueous solutions of these. So if you pause the video here and just take some time and really give this some practice. Okay, I'll go through these answers. I'm not going to go in any detail. This is more just checking your answers. So best way to do this is probably with a table where we can have the anode on the left and the cathode on the right. And there are a couple in this list that I think I'll just make a note on. Pretty normal here. For our ZnCl2, I haven't said here if you'd have concentrated or non-concentrated. So it would be O2 or Cl2 depending on which one. Same goes for KCl. And yeah, the rest are, all you have to do is look at your table and compare those values. So hopefully you're feeling a little bit better about attempting questions like that and getting used to using your data booklet. Which brings us on to one of the major uses of this process, which is electroplating. So electroplating is just simply taking one material and coating it with a very fine layer of another, usually more expensive material. And this has a few different uses, the first of which can be decorative. So if you've ever had a ring which kind of leaves a mark on your skin, that's usually because it's made out of, kind of a monkey metal, as it's called, which is just a low quality metal. And what they do with this is they coat it in something like gold or silver, and all of a sudden something that may not have been desirable, at least initially, can be sold then as a wedding ring or something of the sort, even though after time it will wear. So we can have decorative uses. Another use is for corrosion resistance. So that might be a protective corrosion resistance that looks a little bit like the bumper on this car, which chromium is used to protect the iron underneath. Or we can have a more sacrificial protection in which a more reactive metal is used to coat a less reactive metal. So this is especially popular with galvanized iron using zinc. So when iron rusts, the problem with iron rust is it forms fissures in the metal. It burrows down into the metal when it rusts, which causes structural issues. Now, zinc oxide, however, doesn't have the same property. Zinc oxidizes on the surface, and so what we can do is we can coat zinc onto the iron, and that zinc oxide will oxidize, but it won't burrow down and weaken the metal. So we can use it as a sacrificial protection. We can also enhance the properties of a material here. So like at the top, we can use gold plating where increased resistance or corrosion resistance may be needed, or conductivity. And this often plays into the hands of the other uses as well. Often a coating may have multiple uses for a material that we are using. So our electrolysis has to have a few features in order to be able to do this. So one of those features is we need to have an electrolyte that contains the ion that we want to deposit onto the metal. And the other is that the cathode is actually made of the object that we want to coat, which makes sense because that is where reduction happens. So we usually deposit our metal on the cathode. And lastly, sometimes the anode is also made of the material that we want to plate with, so that the ions in solution are replenished as the reaction occurs, although this may not always be the case. So we can look at one example of this by looking at the purification of copper, which is done through electrolysis. So here we have an electrolytic cell where both the anode and cathode are actually made of copper. Now we're going to have one electrode, the cathode, being made of very pure copper, and then we're going to have the anode being made, as shown here on the left hand side, of an impure copper. Now, what's going to happen is we're going to get pure copper ions move into solution, which is usually a solution of copper sulfate, and then copper ions are going to deposit on the pure copper electrode. And what this does is, as the course of the electrolysis happens, any impurities just fall to the bottom because they're not attracted to go across, and so we get a pure copper electrode that increases in size, and we get the impure copper anode, which decreases in size. And like I said before, this is usually a copper sulfate solution that we use. That leads us lastly to quantitative electrolysis. So using the equation Q equals IT, and that is Q for charge, which is measured in coulombs, I for current, and T for time, that's time in seconds, and current I in amps. We can use this equation if we want to quantify the exact amount that we are going to expect to produce an increase or decrease in the mass of an electrode, especially when we consider the charge of an individual electron. And this is given in table 2 of your data booklet, which is 1.602 times 10 to the 19. So if we take that charge, we can work out how many electrons we have per coulomb. So we just do 1 divided by this number. And so that means we have 6.24 times 10 to the 18 electrons per coulomb. It's a very simple equation, and we can use it to calculate and quantify our electrolysis. We can also use it to extrapolate the factors that will affect electrolysis. So let's have a look at time. Now, looking at the equation, this might be obvious that the longer the time, the more products are formed. We've got Q equals IT. If we increase the value of T, then we're going to increase the value of Q. The second factor is ionic charge, which may not be as obvious from the equation. If everything is kept the same, then the number of electrons that it takes to discharge an ion means we will affect the mass of a given product. You'll see here, if we have a 1+, a 2+, or a 3+ charge, then we have a different number of electrons to produce 1 mole of our product. And so therefore, the higher the ionic charge, the less metal we will form, or the lower the charge, the more we will form, because we need less electrons per mole required to discharge the metal. So here we have an example question asking us to find the mass of copper deposited in an electrode and how that would change if we used a different salt of copper chloride. So we can see that part A is asking us about time, and part B is clearly asking us about charge. So let's have a look at part A. So using Q equals IT and the information from the question, we've got 2 amps, which is our value for I. The only thing we need to convert is 15 minutes into seconds. So we're just going to do 2 times 15 times 60. And that is going to give us our charge in coulombs. And to be able to convert this into grams, we need to work out the number of electrons that we have. So we're just going to divide that by Faraday's constant. And that is going to give us the number of moles of electrons we have. Once we have the number of moles of electrons, then we just use our half equation. You can see here that we need 2 moles of electrons to make 1 mole of copper. So it's a 2-to-1 ratio. So I'm simply going to do 0.01865 divided by 2. And that is going to be my number of moles of copper. Obviously, the question asks for a mass, so I'm just going to use mass equals moles times molecular mass, which is 63.55, and gives me 0.593 grams. Now, part B of this question is asking about the different salt, where copper only has a 1+ charge. So I'm still going to use the same amount of electrons because the electrolysis works for the same amount of time, but now the charge on my copper is different. So the new equation is only going to require 1 electron per mole of copper solid form. So it's a 1-to-1 reaction. So therefore the number of moles is the same as the number of moles of electrons. So all I'm going to have there is just use that multiplied by my molecular mass, which is going to give me my mass of copper, which in this case is going to be exactly twice the amount that I got in part A, because I have half the charge. So these aren't particularly difficult as long as you remember to use your data booklet for Faraday's constant if you forget it. Let's get you doing a question on that then. First question, with all things kept the same, what would happen to the mass of the product produced if I doubled the time? Pause the video here to give yourself a moment for that. Pop them up. A quick look at your Q equals IT equation shows you that it's directly proportional. So if we double the value of T, we are going to double the value of Q if everything else is kept the same. Okay then, what mass of zinc will be deposited if we conduct a 34-minute electrolysis at 3 amps of zinc sulfate solution? Pause the video here. Pop them up. So again, we're using Q equals IT, and as long as you remember to convert your minutes into seconds by multiplying them by 60, you just plug in your values, which is 3 times 34 times 60. That gives you 6,120. So convert that to moles by using Faraday's constant, because remember we want to get a mass, just not the amount of charge, which gives us 0.0634 moles. Then I'm just going to use the half equation for zinc's reduction, and I need 2 electrons for every 1 mole of zinc. So I'm going to do my number of moles over 2, which gives me 0.0317 moles. And then using the molecular mass of zinc, I'm going to find that this should produce 2.072 grams. Fantastic. So as always, guys, you're going to need to make sure you do some questions on all the types of stuff we've done today. But really, you want to get familiar with that table that you get, table 24 in your data booklet, so that you easily tell what's being oxidized at the anode and what's being reduced at the cathode. Thanks again for joining me, guys. Really appreciate all the feedback I've been getting. Please like, subscribe, hit the bell icon. Check out our other channels, they're linked in the description below. Once again, practice makes slightly better.